Welcome everybody. Good morning, good afternoon, wherever you are. We have a worldwide audience today. Welcome to our webinar, White Box Testing and Safety Related Projects with Martin Reininger today. And my name is Klaus Lamberts. I'm co-founder and CEO of the company VerifySoft. VerifySoft hosts this webinar today, but the main person here will be Martin Reininger. He will do the main presentation. Then at the end of this webinar we will have two presentations by my colleague Roland, who is technical customer consultant in our company. And I will give you a short insight into our company. VerifySoft has been founded in 2003 as a distributor for test well tools in Offenburg in Germany, close to the French border. And since 2013 we are owner of the test well tools, which we have purchased from Finnish company Testwell, in particular the code coverage analyzer Testwell CTC++. We will tell you some more about this later. And we have distribution and support of complementary tools such as Grammatic and Imagix. We also provide seminar. One of them is testing of embedded software with Martin Reininger. So we have currently more than 700 customers in 40 countries all over the world, mostly companies which are working in safety critical
like automotive, like aeronautics, healthcare, and so on. So our main tool is Testwell CTC++, is a code coverage analyzer which works for all coverage levels up to MCDC and multi-condition coverage, so all which is required by the standards. And the interesting with the thesis tool is very interesting because it works with all compilers and all embedded targets. Whatever you have, normally this should work. In addition, we have complementary tools like Imagix. Imagix is a tool, when you don't understand your code, this can help you. When you have legacy code, when you have third-party code and you want to understand this code, Imagix helps you with the control flow and then dependency analysis, with architecture analysis. It finds problems related to data usage and race conditions, makes reverse engineering. So when you're a bit lost in your software, Imagix 4D might help. So this is already what I have, my introduction. I wish you a successful webinar and we can switch over to Martin then.
Thank you very much, Klaus. The topic today is the 5 key factors for successful white box testing. Short introduction to myself. I'm in the business since more than 20 years. Started before the year 2000 already, so quite a long time ago. I founded 2018 the Heicon GmbH. It's a consulting company help customers to establish good software development processes, effective and useful in the practical daily work, useful software development processes. The industries are railway, industrial, automotive, and aerospace. And the aerospace is where I have my main experience. Also, this webinar will show you, giving you information based on long time experience in aerospace. Because the difference in the different safety critical industries are that the standards are almost the same nowadays, but the industry with the longest practical history is the aerospace, and I think should try to benefit wherever possible. Just one last word on Heicon. We're doing requirement engineering, test engineering, and functional safety. These are also the main hands-on coaching topics. Okay. Let us start into the webinar technically. First, I want to give you a short introduction on white box testing and what it is and how I see it. And then we talk about the 5 key factors. The first one is how are the expected functional test results determined? Yeah. So are there functional test results there? Could also be the question. So functionality versus or additional to structural coverage. The second point is about normal range test cases. Which test methods you should use to create normal range test cases. The third point, almost the same, but with robustness test cases. And you see here maybe already some interesting point. There's only a difference between normal range requirement-based test cases and robustness robustness test cases, not more. And that makes things also easier. But let us see when we are going to discuss the topics, the details on it. The fourth point of these 5 white box testing aspects is, of course, the white box testing aspect, which is the structural source code coverage measurement. But what role does it play? For what is it there? That's what we should all make aware. Should us make aware. Where is the strength of it and how do we use it? The fifth point is then, last but not least, the reviews. It's always beneficial in any project to even do some review aspects, some reviews on your testing topics. Can be a job for the quality assurance, can be done by the technical guys, and I will show you the benefits there. And last but not least, the take-home message. Okay, the introduction. Yeah, we have this nice testing organization since a few years, the ISTQB, which defines, or a major concern of them is to define terms and make them consistent throughout the testing community. And therefore, it's the first point to look there and say, how do they define the topic white box testing? What is the definition of white box testing in the ISTQB? And that's testing. The testing is based on an analysis of the internal structure of the component or the system. And they have defined a lot of synonyms like clear box testing, code-based testing, glass box testing, logical coverage testing, logic-driven testing, structural testing, structure-based testing. There is a nice joke about it. It's white box testing is actually no difference to black box testing. In both boxes, you don't see it. The box is just white instead of black. Yeah? So therefore, we need a glass box. Yeah, the box has to be a glass box. So we have to be able to see inside, to see the internal structure of what we are going to test. And this internal structure is in practice, what I'm talking today, always the source code. And I'm mentioning that because the ISTQB takes this even wider, this definition. Yeah, so he could think of components or systems of systems where you can have a look into the system and you do not see the source code, you see some hardware elements or some other pieces. So the internal structure of this component or system. But what we are doing here is based on source code coverage, or source code is our internal structure. Yeah. The next point is the V model, the well-known V model. And what I want to focus on is here actually, so first of all, let's go through the V model shortly. You see here on the right side, the testing aspects, starting on the lowest level with unit testing and integration, software integration, then hardware, software integration in an embedded system, and the system testing on the highest level. The left side on the V is maybe a bit special to you, because Heicon is distinguishing between quite strongly between requirements and architecture. This is very, very important from a specification point of view to do that. It makes things much easier, by the way. And system requirements, software requirements, and then on the lowest level there is here requirement as a whole. In the aerospace, it would be low-level software requirements, but as we want to make it generic here, typically you have the software detailed design, which is very often implemented or documented in the source code. So unit testing is on this level mostly against software design, or very often. The system test and the hardware-software integration test is against the system requirements, and the hardware-software against the software requirements typically. And a special case is the software integration testing we will see in this webinar. Important here, the right side testing functionality is increasing when you come from the bottom to the top. Yeah, on system level, of course, you have the highest level of testing of functionality. Yeah, if you do unit testing or software integration testing, you test a lot of design and architecture aspects and very little functionality. Yeah, functionality can be on the unit test area, reading a value, writing a value to a certain register, doing a short calculation. But on system level, you send data to some other system, you receive some information, you calculate something, and you send some information out to somebody else, or you steer a motor or whatever. So this is, let's say, real functionality, customer-wise, customer-specified functionality. This we do not have on unit level, obviously. Not to forget here, the black box and the white box terms. As we said, white box testing, these two levels here, I would call them both here quite white box, or we will see this in a moment, that I want to give you a hint or an idea to distinguish, or to make your mind up about the differences between software integration tests and unit tests, or then combination of it. And of course, on system level or on a hardware software integration level, we are far closer to a black box, gray black box. As a system level is end user testing with the same interfaces as the user, so typically black box. Facts about white box testing, as I have seen it, or I see it, typically it's performed by software testers, software developers, before the software modules unit are integrated. That's the ideal world. Yeah. The measurement of structural code coverage is done by a tool support, so it's not done by just measuring it themselves. There are a lot of tools available. One of them is CTC++, which we will see in the end of this seminar, of this webinar. Then it's a required test method, the white box testing in the embedded safety projects. Performed according standards like 26262, so automotive, industrial, the 61508, aerospace 178, and 50128, it's the railway. And in all of them you need 100% structural coverage to be achieved, which can be different. There are differences actually. It can be a statement coverage, a branch coverage, a MCDC. These are the typical three coverage methods. Due to limited time in this webinar, unfortunately, I can't show you the differences, but you may know of them. Aerospace safety projects do have 40 years plus experience, extensive experience in performing such tests. And I have seen the benefits and the pros and cons of it. And some of them we will just discuss here now, or the most important ones. Also, a fact is that in IT software projects, as a web applications or similar things, or database handling or something, software which is running on the PC, to make it short, there is this structural coverage measurement not really used. If you go into the test theory in books like from the ISTQB, basic software, basics on software testing, or test analyst, or so on and so forth, you will see that this is a really area. The white box testing and the coverage measurement is really strongly used in in safety critical projects and in embedded projects sometimes, but almost as a very little compared to the size of the industry in IT projects. So there is not much coverage measurements there. The aerospace, to focus on them for an introduction, actually, what is their experience of the 40 years plus way of working with unit tests? Actually, 100% structural coverage, whatever it is, statement, branch, MCDC, doesn't alone is not a criteria for a good test. Yeah, finding failures. The code does what the code does. This is mainly the result of such a test. If you would focus only on structural coverage, it is meaningless. Performing a white box test in a team which does not have developed the source code is very expensive. That's where I mean. There is a lot of areas possible where even the software developer who has done the code is allowed to write its own unit test. However, it is better, of course, that somebody else in a development team who has not developed this piece of code does the integration or the unit test, because it's just the guy who has written the code itself does not see its own failures, actually, as we all know, yeah, from doing any kind of work. It's always difficult to see your own failures. It's much easier to see the failures of others. The software integration level is most beneficial. We will see this in a few moments. Actually, what I mean with software integration level is really most beneficial for white box testing. It's not the unit and module level, so the lowest piece. The lowest piece of a software, the atomic part of it is one function, one C, and in C, language C, a function, or in C++, a method. And in C++, it's very easy or very nice to see to decouple the methods from the data in the class. Yeah, is actually making the things more complicated and the unit testing kind of meaningless. So the C++ gives already a hint in the direction of software integration, because at least you get the data and the methods together. And I'm going even a step further with my approach later on. But just to be clear, the unit and module level is meant the lowest atomic level of a language. Yeah? So measuring the structural coverage can support the argumentation that the used compiler does not introduce failure into the operational object source code. This is a not very famous point. A lot of people are not aware of this point at all. And these people are testing code coverage mostly on the PC and do not care about their compiler settings and the right cross compiler. They take any compiler running on the PC. So they are decoupling, let's say, the testing from the target to the PC complete with respect to the compiler completely. And this is wrong. If you can prove 100% code coverage with your compiler correctly in use, correctly used, ideally on the target, then then you have a good argument in place to say, okay, I have tested that the compiler is not introducing failure into my software. Yeah, because certify or classify or test a compiler completely is impossible. But for a piece of software, if we really fully test this software, we have a good confidence, acceptable confidence to say there's no additional failure introduced by the compiler. The topic in itself, we can't discuss it completely in this webinar. If you're interested, please feel free to contact me. So now, first point, how are the expected functional test results determined? After the long introduction, creating the tests with only measuring the coverage is meaningless, as I said already. Therefore, the first step should be always to create test cases focusing on the functional aspects of your unit or your integration, software integration modules or integrated modules, your functional modules. And then you measure the structural coverage, but you're always focusing on the functionality. And believe me, if assessors or externals have have experience, they see what you have, whether you have followed this approach here in this order, first the functionality and secondly the structural coverage, or which happens sometimes you focus your testing only on achieving the structural coverage and don't care on the functionality. It's for experienced people, it's easy to see what was in the focus, in the main focus of your test. It should always be the functionality. Further points will come on that. To create a white box test, not on the lowest possible entity, the method or a function, so instead you should define logical software entities and perform an integration test on it. So you should add all the software modules or software functions together which form one functionality. For example, handling some error cases. Yeah, you have some error handler and you send some data to some other interfaces and you switch on a lamp and you do whatever else. Such things can be tested, the software logic of it, integrated in one test. And that's the integration test I'm talking talked about already. And this is really beneficial because on this level you find the problems, yeah, the logical software problems. There are not so many problems compared to this in the unit or the module individually. These kind of failures in individual units and modules are discovered by the developer itself during integration or during review, yeah, and the testing is much stronger on integration level. So the second point, define a specification which helps the tester to identify the expected functional test results. There are not always requirements. Therefore, I formulated in this term, define a specification. Never use the source code as the only source of information for the tester. That's the point. So there are some textual description in the source code. There is some architectural diagrams, at least, yeah, there or should be there for forming the tests. So always push yourself to give the testers some more information than only the source code for unit testing. So not the other way around. This was exactly for the first point above. Here, so always functionality before coverage measurement. So, and how are they defined, this coverage, this functional results? Yeah, by specifications and not the source code alone. Now making a diagram on what I mean with integration versus unit testing. Here, this brown box is integration testing. There are several C files together with a lot of functions forming one functional block, and there's another functional block, and they are put together, and an integration test and software integration test is done to test the logic and the data flow through these systems. Yeah, for example, here from the top level through here, there. That's what you should do, and that's where you find the problems. Compared to it, the unit and module test is either on a single file, a single C file, or even on a single function, actually in a file on the language C. The benefit of this right side is you're getting much faster. So writing unit tests on this level is getting quite fast. It's quite easy. You can put unexperienced people there. They're doing pretty well your unit testing. Fair enough. But you find not many problems. Yeah, you do just the testing more for formal reasons. Here, it takes longer time because to specify these tests, to form these brown boxes here, this is the big challenge, and there you need experience. You need to understand your software architecture. You need to have experienced testers to form this correctly, because if you make it too big, then it takes too long to do the testing, and it may not work then actually in the end. And also to create these tests takes longer, but the big benefit is you find problems. Yeah, and yeah, here the stubs or mocks are defined outside of these brown boxes, of course. The big benefit is here if you are able to define such tests in these brown boxes here that you get then, that's really the experience, then you can link them to functional software requirements. And that's what we want to do. We want to test the functionality and measure only the coverage additionally. Yeah, we do not want to test the structure of the source code alone. Good. That's to the functionality. The second one now, the normal, and we take the third one just with us, then the robustness test cases. The most valuable approach is to use for unit and module testing one of the following informations to be tested: functional requirements, architecture and design, informal developer information about the tested software, as I mentioned just before already. And then if you have this information, some parts of it available, then you're going to do as a tester equivalence classes. And as you have normally more than one input to a system, you do combinatorial testing. You use test methods like pairwise testing, and there are actually some more there. But if you want to see all test methods, then you have to come to the test seminar, as Klaus mentioned, actually, the next one in April in Offenburg. Then there we discuss all possible or a lot of famous possible test methods. The point is equivalence classes is just to make it simple. You have an integer value and something functional happens if the value gets 10, something different happens if the value gets 20, and it's all the same between 20 and 32,001 something. Then you would use a value from the block 0 to 10, a next test case 10 to 20, and the next test case some value out of above 20. That's the equivalence classes. Boundary testing is actually very valuable as well to test around these boundaries, 20 as a 19, 20, 21, and so on and so forth. Pairwise testing is a bit more complicated. To read the feasible books or come in the seminar. Important is actually more important than such this method is then in combination, or the really big value you get is if you combine this with error guessing as a mental attitude of a tester, not as a test method. Error guessing is not really a test method. It's a mental attitude of a tester. He wants to find problems. He wants to find failures. And if you can combine this, that's the greatest. Yeah. And you have a specification. Do not forget. You test. So that's the normal range. And then for the robustness testing, once you have finished your testing with the normal range, so your specification, whatever it is, yeah, here the normal range based on available specification, documented structured source code, then you should review the create integration tested, and you apply then experience-based test methods. This means you're going outside, or you're going intentionally outside of your specification or to the real strange or stressful scenarios to your system, which you cannot specify in, or you have not specified typically in requirements, and which is just stressing your system. So you try to stress your system outside the specification or close to the boundaries of the specified values, and that's called robustness testing. And here it's even more important to think about error guessing testing in order to effectively identify missing tests. So in these two combinations, first of all, test what is specified, and secondly, question the specification more or less by robustness testing. This is very, very, very helpful, and this is the added value. And actually, robustness testing is very important, especially on the lower unit and integration levels. And that's the reason actually why these test methods, these test levels are there, because in a fully integrated system on system level, you are not able to stress each of your modules or your components fully. Yeah. So a lot of robustness cases you can't test on a fully integrated system. So therefore, we need the lower level testing. So this is the main reason, is the robustness reason. So, and now, after all that, so we know functional specification and we know what to test. We have test methods for normal range and robustness test cases. Now we think about the structural code coverage, yeah, the typically white box testing, yeah. So now we say, okay, we are going to measure with these tests the structural coverage. And why we are doing that, yeah, there is a diagram I recently created. I think it makes it quite visible what is going to happen. If you think about test coverage or requirements coverage, then you have one weak point whatever you do here on cost and time, however long it takes, yeah, you will never reach 100%. There is no 100% software test. There is no 100% specification. That's the weak point of these methods. The benefit of structural coverage is that the strength of structural coverage is that this is exactly definable. What is 100% structural coverage can be defined on a mathematical way. In a minute, we see this on a next slide, and this helps you to minimize this gap in the end. And this diagram just sees in the beginning and early project phases, of course, the gap, what you want to reach, the 100% test coverage, requirements coverage, or structural coverage is bigger. And as you go on with your project, you minimize it, but you get it not to zero, as it is an asymptote here. Yeah. So you're just able to minimize the remaining steps. So now when we're going to compare these methods, the requirements, the dynamic testing, and the structural source code coverage, then you see the strengths of requirements are functional description. The weakness is the completeness. The same for testing. Testing, the functionality, this is the strength of the dynamic testing. The weakness is the completeness. And for structural source code measurement, it's the other way around. Detection of functional failures, almost impossible. So yeah, almost impossible. And the strength is the mathematical completeness proof. This is the strength of structural coverage. And the original idea of the aerospace was, believe it or not, to exactly therefore combine or use the structural coverage to find holes in your requirements and in the testing. The point is just, as you may know or you may experience, the structural coverage testing is mainly done on unit level. And the unit level, as I said, is the lowest level. And on that level, to define requirements is not really effective. It's done in the aerospace, but with a lot of other problems. And what we would like to do is to measure the structural coverage on higher levels to get this this combination with the requirements, to be able to measure it on the requirement level. And therefore, we try to go up in the testing hierarchy at least one level, as I promised, or as I said, to the software integration level. And later on in the next presentation from Roland, you will see with tools like CTC++, you can measure the code coverage even on the hardware, on hardware integration tests, or even system tests to some extent. And that's where you can get the benefit of a structural coverage. And with future non-intrusive code coverage measurements, it will be even more beneficial to test on integration and system level, because the weak point is we need some instrumentation, as we will see from Roland. And this instrumentation of the source code for measuring structural coverage results in limiting your possibilities on the system and hardware software integration level testing. But that's what we wanted to do, and not this just getting code coverage for any price, just do it. That's not what we want to do. Okay. Last but not least, the last point is after we have now functionally tested our system with systematic deriving test cases, normal and robust, and measuring the coverage, finding the holes in requirements and tests, or the source code. Actually, of course, that source code is of course as well a result. As a source code you don't need. The last point is review. How do you successfully and efficiently perform test reviews? This is really a strong point. The quality of testing, if you look into projects, or if I look in my history back, the strengths of testing is good test cases or good tests. You always have there. You get it in these projects where you do at least some reviews. So you may argue now, we have done already the testing. Who should review these tests? We do not have the time and the money and whatever. And we are not functional safety relevant, maybe. Yeah, so we have no need based on a standard or a norm. Then my argument would be, yes, but you are ISO 9000 certified. So, and in an ISO 9000 certified company, you do everything in the software development in a 4I, or even there is the 4I principle there. You do all your steps in a 4I principle. And also the testing should be done in a 4I principle. This means your quality department can do a checklist and can review maybe 10% of your tests. And my experience is if you review 10% and you have some experience with selecting the right 10%, then you find there bigger quality holes. And then you're going, if you find bigger quality holes, you're going to review more, as you do in normal quality assurance processes in the mechanical area or production area. You're also not checking each of your produced systems, whether they are correct. You do a lower part out of it. So this is one point. So you're going to review some of them. And the second is you do a checklist. Please always use a checklist for reviewing your tests. Here I have mentioned 5 or 6 points to give you an idea of what should be there or what can be there in a test review checklist. But to be honest, to make it really effective, you need to adapt this checklist to your projects. As the best review checklists are always the ones which are made for the individual projects. Each project has its own specialities, or each company at least, maybe not each project, but each company. So, and if you go to adapt this to your needs, then the checklists are really powerful. The testers know about the checklist before you start even testing. They get the checklist, so they know what is the focus on it. So, and this means in this way you can ensure quite a high quality. So finally now the take-home message. Performing white box testing just with the goal of proof the structural code coverage is meaningless, as now mentioned several times. And again, it's seen so often, it's done so often. People, even assessors, are happy to have 100% source code coverage, yeah, but first of all, 100% source code coverage is to be questioned, yeah, because if you're not using the debugger, normally you have no way. There's in each software some software parts which you can't achieve, yeah, or you can only test if you have a debugger, and the debugger should not be used for such testing. Yeah, that's also from experience. People, they don't like the debugger in such test environments. So doing only the coverage is not a good idea. The beneficial white box testing is driven by proving the functionality. And there are 2 aspects of it. First of all, you have some specification, what you're going to test. You're not just testing the source code as itself. Yeah, you define functional expected values, what you expect from this test. And secondly, you are not using the lowest level, the unit or module level. You try to integrate and build functional software blocks, which are represented in requirements. And in this way, connecting requirements and testing together and test them. This is by far the best way of make use of this testing and not produce unit tests just for any assessment. The structural coverage provides hints towards the completeness of testing and specification. So if you do it like explained here, focusing on the functionality, and then measure the code coverage, just let it run beside you, and from time to time you have a look on what you have achieved on structural coverage, and of course you look then into the test and into the coverage, as we will just in a moment will be seen by Roland. He will present us such reports. You have a look there, and if you have then holes, coverage holes, then you start thinking of, is it due to a missing test case? Is that a requirement not complete? Or is it really source code we don't need, we can remove, yeah? Or actually the 4th point normally is safety aspects like defense programming and things like that. So normally you never ever have 100%, you have not 100% coverage, yeah, due to these reasons. Last point, review of the test is very effective. A review of a test is very effective mean to keep a high quality of tests. Yeah, as I said, review, if you have a process in your company that from time to time you go to review your tests, significantly increases the quality of your testing department gets feedback, and yeah, you have a high quality of testing. If you are outside of safety projects and you have not the need to review all tests, then ask your quality department or do yourself at least 10% of your tests, and depending on the results, do either more or less reviews. Okay. Questions, as I said, after presentation from Roland now. I'm finished with my presentation. As you see here, my contact details, please feel free to ask if you have any topics around these areas. And now I would like to hand over to Roland.
Thank you, Martin. So hello, everybody. So you should see my starting screen, correct?
Yes.
So while I'm using, let's say, 10 minutes so that we still have some time to discuss things you put right now into the chat from Martin's presentation or my presentation. And I will take these 10 minutes to give you an overview what a code coverage analyzer is, or what our code coverage analyzer is, how it works, and give you a preview of results you can achieve with that. So let's go into the presentation. Here are 5 bullet points. They are there not to describe what CDC++ is, but let's say you know what a code cover, you want to measure code coverage. So you look for a code coverage analyzer. And there are lots of code coverage analyzer results in Google, and you see a lot of them out there. And these 5 bullet points make the difference maybe to other things. So if you say, okay, one of these points, that's what I need, then you're right with us. Let's jump into it. So our code coverage analyzer works with all embedded targets, or is for all embedded targets. That means that you are enabled to run the tests on your target, not on a host only. So we use the method of instrument the code, and wherever this application runs, and even on a microcontroller, when it's running, you can gain coverage data. The second point, it works with every compiler, cross-compiler. It has to work with cross-compilers as well to make an application on your target. But that also means that it's not dedicated to a single compiler or to a unit test framework or whatever. So, but it's designed, TestWell CDC++, to work in almost every environment. It's done by configuration. And as this product is in the market since 30 years already, we have a lot of setups of such configurations so that we expect that you get it up and running very quickly, even if it's based on configuration of your compiler, of your build environment, and so on. And the second point with this is that you do not have to purchase for each compiler for each target. If you decide to use TestWell CDC++ within the licenses, you can use this with every compiler you make it work, or for every target that it works with. So it's not bound to any other product around in your tool chain. It's compliant to safety critical standards. That means, so what Martin mentioned is, with code coverage, we get a method to measure completeness of tests somehow. And depending on the safety class of your product, you have to achieve different levels of code coverage. And all these levels mentioned in the safety critical standards can be covered by our tool. So it's depending what you're choosing. Yeah, and it's all in. The fourth point is an advantage that CDC++ works with low instrumentation overhead. As we support the execution of instrumented code on a target, we see that we have limitations in memory in such devices. That's why we have to take care that we don't have too much code bloat, that it can run on almost every target, but we also have different methods to run different workflows. So depending on the capabilities of your target, on the limitations of your target, we can adjust the way we measure code coverage. So it's works quite good with limited devices, but for sure you need some extra space to bring in the instrumented code that it's a little bit more code than your original code. CDC++ works with C and C++ as the language where we can measure code coverage. That's the main focus of the tool, and it's in the embedded market. It's 90% of the projects are in C or C++. We have add-ons to enable measurement on Java code and C# code. So if you have some code beside your project with these languages, then you're welcome to take a look at CDC++ and use it for these languages as well. So there's a lot about targets on this slide, but if you don't have an embedded target, you want to measure code coverage on a host, for sure you can use CDC++, but it's not this advantage or where it is designed for, but it works. So, but there are a lot of other tools around in the world that you can maybe use. So how does it work? How do we measure code coverage? How do we do white box testing? When we talk about testable CDC++, it sounds like, okay, this is a product. I have a setup and I have one tool. Maybe it has a UI, but it's not that way. It's a collection of a lot of tools, and that's for good reason, because at the end, we execute command line based tools that are easily integratable in your development tool chain. And when in the next slide, I show you in a sample how we do this. So, but when we look on the development tool chain from our tools perspective, then we can say it's done within 3 stages, 3 steps. And the 3 steps are before and after testing. And the very important thing and the very good benefit of testable CDC++ is that we don't care about testing. So it's all about testing. We measure how your test flows through your application, but we don't care how you test. So we can use it for unit tests, for integration tests, for whatever unit test work you have, or even for system tests. It would work. Testable CDC++ only takes care for the first step before the test. That's the instrumentation. That's when we compile the code. Then you see in the blue box some names of tools that are inside this collection. Then you do the test with this prepared code. And at the end, we collect all the results and build some reports. And now let's have a look how this works. So this is a normal way how you develop your code. On the left-hand side, you have some source code. You will compile this code to an application. Let's say it's a Hello World exe. You do some tests. You have some tests, and the tests fail or they pass. And at that point, it's interesting, and Martin mentioned it already in his part of the presentation. We don't talk about the result of a test case. Is it a good test case, a bad test case? Is the application good or bad? Doesn't matter when we measure code coverage. This is for another purpose. We look if the tests cover your code. So if all tests fail, you still would have some code coverage. So these are different things. So and our purpose is to see, okay, is this code touched by some tests? Is every code touched? Okay. Now we we want to do some code coverage measurement. Then we use, let's say here, the tool CDC to instrument our code. What is instrumentation? Instrumentation is that we inject something in your code, in a copy of your code, to make it visible that the test touched this part of the code. And let's have this sample. We have a decision if A is lower than 10. And this is modified and extended to the code below. So you see the original code is still in there, as we have to ensure that the instrumented application works the same way as the original application. But it's extended with a ternary operator, in that case, of a decision here, and we count the truth counters and the false counters. So whenever this is true, a lower 10, then the first one would be incremented, or the second one if it's false. So the function of the lines of the code is the same, but it has an additional ability to count. And here you can exactly see what is the instrumentation overhead. The first part is the thing we introduce into the code. And then we compile this modified code. We put it in a file, what we did. And the second part of the instrumentation overhead is a runtime component that makes the tool able to count. So now in the second step, you do your testing. And with the testing, it's automatically counted. And after the testing, in the third phase, we use tools to build reports based on what we instrumented and what we have counted. And we can do this, the result can be an XML report, for instance, where you can proceed with the result. Maybe you have a dashboard in your build system and your CI, and you want to show some figures somewhere in a graph. Then you can build an XML report and do some coding on this. Or we talked about white box testing, and we want to see, do we have enough tests? Then we usually create, as a result, an HTML report that combines our test results with the original source code. And the next slide, we see here now how it can look like. So this is an overview report about a regulator C file. And we have instrumented for multi-condition. That's a very high level of instrumentation, code coverage level. On the right-hand side, you see the functions, lights, close windows, that are inside this regulator C file. And the bars, they show how much coverage we have achieved. Let's say for the function lights, it looks like we have 75% achieved for multi-condition coverage. And the 75% is the result of, we have 6 out of 8. So what's the 6 out of 8? When we drill down, so we have a link on the lights, on the function name, we can drill down to the source code. And now you see already that we have some background colors here in the source code, where we can easily see the green ones. Yeah, it's easy, it's executed. The red ones, it's not executed. And we have some figures here on the left-hand side. And when we count them, 1, 2, 3, 4, 5, 6, 7, 8, these are the 8 counters we have inside there. And we see that the 6 ones are greater than 0, but we have 2 red zeros here. So our tests are not enough to achieve coverage, because we need some more tests to get these zeros something bigger than 0. So, okay, what happened? What can we learn from this report? Okay, there's a function lights within regulator C that was 14 times called. And this function lights has an argument called goal. And then we have some decisions here based on this argument goal. So if goal is off, on the left-hand side, we see nobody turned the lights off. It was never true. It was 14 times false. Okay, easy. We need a test where we say lights turn goals off. And then the next line would be green, and this counter would be 1 with this single test. But then we still have not coverage, as we have kind of a hidden branch, because we have here the argument goal with 3 possible values, off, on, and dimmed. But let's say you call this lights function with something else than these 3 values. And this is the test case you would need in addition to achieve 100% coverage for this function in this C file. And that's the way you do work with the result. Okay. When we take test.c++ in the middle and look around in the landscape a little bit, what we have there are a lot of IDEs. So if the developer wants to do code coverage or invoke this within his environment, he has a Workbench or Visual Studio or Eclipse or something else, it's easy to, we have prepared such things, but it's easy to build such things as well. You can integrate it into your workflows Doesn't matter if you run it on your machine, if you have continuous integration on a build server, in the cloud, wherever. And as we mentioned in the first slide, it's for all targets and all compilers. If you're interested, so how can you start with such a tool? You do not need to fill out a 10 pages form to say, okay, can I do this and that? Our approach is different. We have, on our webpage, you will find a form, and you can say, okay, I want to do it. I have some time. That's what the only cost you have is your time. You need a project to verify the result you want to achieve, and then you can start. And we offer a free tool evaluation with a full support, and that's for some time, let's say 2-3 weeks. You can test with the tools, and from our experience, this is enough time to get confidence if this is the right tool for your purpose. And so we have still time, Martin. I did it in the time. I'm finished with my part. Thank you. So the questions.
Thank you very
Martin?
much, Roland. Yeah, we have
Okay,
three questions so far. The first one is quite correct, or quite a nice one. Since achieving 100% coverage is practically difficult, is it advisable for a project to define a coverage limit of, say, 97%? That's the question. The limit, as probably I mentioned in the presentation, I would not actually define any limit there, because you can't. Yeah? But the experience clearly tell you in such software integration or unit tests, 95% plus is possible. But it doesn't matter whether you achieve 97 or 96 or 95 or 98. Anyway, you have the remaining coverage, the remaining source code to be explained. Why is it not covered? Why is it okay? Why is the source code still fine? So there is no limit in this way necessary. The next one is for you, Roland. Is the CTC++ certification qualified or certified to ISO 26262? Your turn.
Yeah, you might, or you. Yeah, certification. That's a question we hear a lot. So people are running something in the automotive sector, like this ISO standard is, and they say, okay, I need a certified tool. We work with tool qualification kits. So we think you use our tool in your environment, and we have to take sure that it works in your environment. So there is no certificate for the tool itself, but we give guidance and additional tools that you can prove within your environment that it works as expected. So there is no ISO certificate. But you provide all the data. You provide all the data to the customer, isn't it? Exactly.
Yeah.
So this tool qualification is even better, because that's a proof that the tool works properly within your environment. When you have the ISO, the certification says only that it works properly in the environment which they have tested. So the tool qualification is somewhat more, but if you need this certification, we can do this as well. If this is not a problem. It's a kind of money.
This is a topic in itself. We can do a new webinar actually on the tool qualification. It's a quite complex topic in itself. As Klaus mentioned, actually the tool qualification for you in your environment is technically even the better one. Yes. And definitely also higher rated in ISO 26262.
That's what we support. Yeah.
So the next question is a quite long statement about the implementation, the testing on C files, as my brown boxes, if you remember. And Zoltan, he said, there is it correct, the understanding that in the integration test you don't care of the implementation in the C file? You focus on the header files. And that's right. Actually, this is from a development point of view correct. And only if you measure then the code coverage and see holes, like you have seen from Roland, then you do a kind of glass box. Then you look into your box, and that's the idea. First of all, you close your box, you do your functionality. What do you expect from this piece of software you're testing? And in the end, you open it up and see whether you have achieved everything what is inside the box or not. Roland, the last one here, how would you test for code coverage in an inline function defined in a H file? I think you can, I don't know, can you measure the coverage in a header file if there is source code there?
Yes, you can measure in a header file, but usually you can decide in which files you do it. You have some system headers you usually don't want to measure, but if you have maybe custom headers, you want to measure code coverage in your code. But there are a lot of headers around in a project, system headers, and usually you want to really decide on your own which files you want to test and which ones you don't want to test. And you can do this by some parameters when you instrument the code to decide I want to instrument this, or you can exclude files when you create the report. So then we have...
yeah, I have to check actually the second last question. In a development process, you do typically use the test reviews. It sounds a bit like a milestone or a pull request checklist. Or did I misunderstand? It can be used as a milestone. Yeah, there are scenarios where you have to present everything reviewed, and and if then assessors find problems, then the first guy who is blamed is your quality guy or the guy who reviewed the test. Yeah, so this can be reviews. I argued more for having just quality there in your test. Yeah, use it as a quality measure to improve your tests, or to know that you have good tests done. The last question, a bit of a tricky question. We use bullseye.
Not tricky.
It's not tricky. Yeah. It's the same one.
So it's for you.
Who is you? It's me. It's me.
It's Roland,
it's you or it's me? Or
it's you. I can
tell something.
You can tell. Okay, let's Klaus.
I can try. If there's not enough, you go, Roland. So yeah, a lot of code C++. Okay, you can use bullseye, but it depends on the coverage level you need to prove. Bullseye is good for low coverage levels, such as statement coverage, but it doesn't provide multi-condition MCDC coverage. This
modified condition
decision coverage, yes. And if you are in a safety critical development, like have ASIL-D or ASIL-C project, you need to prove MCDC coverage. Then bullseye is not enough. This is one advantage of CTC++. The other one is you can go on the embedded targets, but I think maybe you don't have, then this is not an advantage for you. The main advantage is the coverage levels. We are higher there.
But why would we use CTC? So my answer would be, so we are not the ones who say never, you don't have to switch. If you're happy, never touch a running system if it works. But if you get in some troubles somehow, we see other products that you say, okay, my build time is too long, whatever trouble you have. And if you're forced, annoyed enough that you say, okay, I'll look around, is there something better? Then you should do a competition between different products, and we are happy if we are one of this. And so you should choose that fits best to you. And if it's CTC++, we are happy. If not, it's okay. So if you say, why would we use CTC++? If you're happy with bullseye, why should you switch?
Keep it.
But keep it as simple as possible. If you have troubles with a tool, if it's too complex, if you have really concerns doing it every day, then have a look at if you get something better.
And another thing could be the coverage of the compilers. Currently with bullseye you have certainly a compiler which is covered by bullseye, otherwise you wouldn't use it. But when you have a new compiler in another project which bullseye doesn't support, CTC will support all compilers. This might be another advantage. So I think it's enough for this.
Great, yeah. So answered all the questions. We are 5 minutes over time, so
it's okay. That's in time.
It's in time. So and still all the people are there. So thank you very much to all participants to this webinar. if there's no further questions, there's coming the further. Thank you already. Then we're going to close this webinar now.
If you have any questions concerning these topics, you can contact either Martin or Roland or myself. You will find the contact data in the mail we will send you. And I, on behalf of Roland and Martin, thank you very much for your participation, and yeah, have a nice end of the day. Thank you very much, and hope you see you soon somewhere.
Thank you very much. Bye-bye.
Bye-bye. Bye.